Radiation video number 1. All right, so in order to start this self-study unit, we are going to be looking at a variety of things. And today we're going to primarily be focusing on some fundamentals of radiation. So the first thing that we're going to kind of go through, and we're going to go through it fairly quickly, are just some definitions that you need to know. So the first you might actually recognize from physics, and that is the electron volt. And as you can see here, it's the amount of energy needed to push an electron across a 1-volt potential. So like literally what this means is if we were to take two metal plates and essentially apply a 1-volt potential, and then here's where it's being grounded, and we take an electron here, that electron is going to require some energy to push the electron across. And so the amount of energy needed to push this electron from one place to another with a 1-volt potential is the electron volt. In this context, we're probably not going to use electron volts much. We're going to use the mega electron volt. So 1,000,000 electron volts is the kind of energy we're going to be taking a look at. All right, another thing that we should know, the difference between non-ionizing and ionizing radiation. Most of what we have looked at this point have been non-ionizing radiation. So radiation that doesn't have the ability to ionize matter. Versus ionizing radiation, the radiation that takes a neutral atom and strips an electron off it. So if I have some neutral atom, for example, let's say carbon, if the ionizing radiation comes in, it's going to actually strip an electron off it as it runs through there. And so it has enough energy to do that. So when we talk about like the minimum energy needed to do that is 2 to 35 electron volts. So that's photons or wavelengths of light that are under 300 nanometers. But I really like this particular view of the electromagnetic spectrum. And the reason I like it is because it really, notice all this overlap in areas. We like to think that everything is defined, if to be, for example, an X-ray, you are very distinct from a gamma ray, or you are very distinct from ultraviolet light, and that isn't actually the case. And so we can have X-rays that have less energy than ultraviolet light, for example. And so I just want you to kind of notice this because that's going to start playing a role for us later on. But if we want to take a look at ionizing versus non-ionizing radiation, the ionizing radiation, I had said is about minimum energy of 2 to 35 electron volts. So here is our electron volt. You notice this is 1 electron volt. So we're really looking, somewhere here and up on there. And so there's some ultraviolet light that could be ionizing and some that isn't. It's just a matter of if it's able to strip off an electron. All right, moving on. What causes radioactivity? Many of you have probably learned this in your Chem 1 class, but essentially it has to do with, it has either too many protons in the nucleus. Think about that. If you have, say, uranium-235, you have 92 protons, positive charges in the nucleus. And when you start getting too many, there's only so much energy that can hold that together. And so it becomes fairly unstable and starts to spit stuff out of the nucleus. Or it has the wrong proton and neutron ratio. It turns out that those neutrons can actually allow more protons to exist in the nucleus, but it has to occur in a very specific ratio. And if that ratio goes awry, we're in trouble. Another thing that could cause radioactivity is an element that maybe doesn't have too many protons or the wrong proton to neutron ratio. If it's exposed to neutrons inside the core of a nuclear reactor, which we will talk about later in this self-study course, or if it gets in the path of a high energy charged particle beam. So you can cause something to become radioactive. But here's a super crucial thing for you guys to know just as citizens. First of all, if I take some substance, just some, we can be very generic here, some substance, some non-radioactive substance, and if I expose it to gamma rays, that's a Greek gamma, or X-rays, we're going to see over the course of time that those are not really too distinct from each other, or beam of beta particles, which is a type of radiation, or alpha particles. So basically, if I shoot radiation at some substance, and this is what's super important, in the end, it is not radioactive. Just because I shot radiation at it, there is no radiation emitted from it after. Really, really important. And here's why it's important. This is used in a lot of things. So, for example, this is how they sterilize, those of you going into medicine, this is how they sterilize medical instruments. So, for example, they literally take the medical instruments, they put them under a high dose of gamma rays, and then they seal them up so that they're no longer exposed. So when you're in the operating room, they open it up, and that's the first time it's being exposed to anything. It has killed anything that might have been living on that medical tool, but it has not made the medical tool radioactive. Or this is also used for food sterilization, to kill off things that might be growing on the food. Now, it might have some chemical changes like cooking does, right? It might change the consistency of it or something like that, but it doesn't make the food radioactive. None of these make it radioactive. However, if I take that same substance and I expose it to some energetic neutrons, for example, from a nuclear reactor, or some very high energy charged particles, then I could make that substance become radioactive. And if it becomes radioactive, then perhaps it might now give off a gamma ray or a beta particle or an alpha particle. It depends what happened to it. So that's something, that's just really important. You have to really work hard to make something that wasn't radioactive become radioactive. I mean, putting something into the core of a nuclear reactor is not something that happens every day. So just kind of be aware of that. All right, different types of radioactive decay. So if our nucleus has too many protons or the wrong proton to neutron ratio, stuff might happen to help it become a little more stable. And so one thing is that one of the neutrons, N is for neutron, proton, electron, one of the neutrons in the nucleus might actually break apart into a proton, and this isn't, it is an electron, but it's a high-speed electron that actually leaves the nucleus. And that's important. And since it's leaving at a high speed, that's actually the beta particle. One way you may have seen this written before, this is our little abbreviation, right? So no protons, one neutron, can break apart into a proton, which is just a hydrogen ion, and a 0, -1 E. This is the beta particle. Or you could write a neutron breaks into a proton and a beta particle, which helps to explain it being this high-speed electron. So this occurs, we talked about this proton to neutron ratio. If there's too many neutrons present in the nucleus compared to the protons, then one of the neutrons can break down and it turns into a proton staying in the nucleus and this beta particle, which then leaves. So for example, here's an example of phosphorus 32. Now you'll notice I didn't even write this down here, the atomic number, because you can look off a periodic table, so it's assumed to happen. But it could break down into sulfur 32 when it ejects a beta particle. And so that beta particle is emitted. And so this actually, hold on, I got to grab my periodic table. Oops, not what I wanted to do. Hold on. Let me find my periodic table. Got it. Got my periodic table. Sorry, I didn't have all the atomic numbers memorized, which is so strange. But anyway, so here's phosphorus. Phosphorus is 15. And so in emitting that, it actually turns into sulfur, which is 16. And you might recall from your Chem 1 days, the numbers on the bottom have to equal here, as well as the numbers on the top have to equal on each side of the arrow. Another one, for example, is scandium, which is atomic number 21. Scandium will also release a beta particle. And so if it releases a beta particle, that essentially means a neutron turned into a proton. In the nucleus, it becomes titanium, number 22, and it becomes titanium 47. So that's one, just a couple examples of that. Now, positron decay. Positron is the antimatter to a beta. So if a beta particle is 0, -1e, a positron is 0, +1e. It is essentially a positive electron. Well, it turns out that if you take a proton and you add a very specific amount of energy to it, 1.022 mega electron volts, what will happen is it will actually separate a beta particle, which is this, from its antimatter. And I actually spoke that incorrectly. It won't separate it. It will E = mc² it, right? Einstein's equation. It will use that energy to turn it back into mass. When antimatter particles come together, they annihilate each other, and they give off a very specific amount of energy. In other words, their mass disappears when they annihilate each other, and they give off energy. Well, that amount of energy is 1.022 mega electron volts. And so when these two actually come together, they actually end up giving off in two directions, 0.511 mega electron volts in two different directions. So if this is how much energy is given off when they annihilate each other, that's how much energy you have to put in to recreate them. So in positron decay, that amount of energy essentially creates the two antiparticles, the beta minus and the beta positive. And in this case, the beta positive is ejected. Now, this isn't truly a beta minus because it's not a high speed particle, and it doesn't leave the nucleus. You guys, that's really the difference. An electron, or not the nucleus, doesn't leave the atom. An electron stays in the atom where it's supposed to. A beta is an electron that leaves, and that's really the key. And it has more energy, and that's why it's able to leave. So when I'm trying to use this to show the antimatter properties of it, but this electron stays. The beta positron is the one that is ejected, and so as a result, if you look at what happens, the proton and the electron actually turn into the neutron. What? Right? Here's a proton plus an electron. Take a look at what happens here. And I apologize because I wrote that hydrogen. Should have a 1 up here. 1 plus -1 is 0. 1 plus 0. Look, here's your proton plus electron turns into a neutron. And this is really, I probably wrote this wrong, an electron that stays as a result. So that is essentially what happens. So this occurs when too many protons are in the nucleus. Because what does it do? It turns a proton into a neutron. And that's what's going to happen. Oh, geez. This is I apologize. I have a typo, and that's why this is screwing up. This is supposed to be beta positive. That's what leaves. So the beta positive leaves. The proton and electron become a neutron. What a mess. I am so sorry, but I'm not redoing the video because it's not worth it. So to review, proton plus energy creates two antimatter particles. The proton and the electron combine to form the neutron, and the beta positron is ejected. All right. Happens when there's too many protons in the nucleus. So here's some examples. I'm not going to go through all of them, but in a similar vein, if you take carbon 11, just an isotope of carbon, if it emits a beta positron, 0 positive 1e, you end up with boron 11. Or if this gives off a beta positron, you end up with Ru98 plus a beta positron. Or if fluorine 18 is also a positron emitter. I bring this one up actually because this is used for medical imaging purposes. So you future doctors or nurses or radiation technologists or anything like this, this is a super important radioactive isotope that is used, and has a fairly short half-life, so it's important that like the hospital is near where that radioisotope is being produced. Okay, moving on. So we had beta, we had positron, we have electron capture. It's sometimes called K capture because K is a way to refer to the inner shell of electrons. And notice, this is an alternate mode to beta positron. So it occurs, again, just like in positron emission, when there's too many protons in the nucleus. And essentially what happens here is that some electron combines with a proton in the nucleus, and it produces a neutron. But the key here is that this is an actual electron from outside the nucleus. So it grabs an electron from outside the nucleus, reacts it with a proton, and as a result creates an extra neutron. So it decreases the number of protons but increases the number of neutrons. But the key with this one's often accompanied by an X-ray or a gamma ray, releases some energy. That's essentially what that means. So an example might be beryllium 7. Beryllium 7 will, capture an electron. So let's write that. And it will end up producing, if I could do the math correctly, 4 plus negative 1 is not 5, but it is 3. It could produce lithium 7, and then it'll typically give off a gamma ray or an X-ray. So that's just an alternate mode for that. All right, gamma ray. Moving on. What's the difference between an X-ray and a gamma ray? If I scroll back, oh, look. They overlap, okay? X-rays, you'll notice from that chart. So X-rays are often, lower in energy, and gamma rays are often higher in energy, but they overlap. They're both ionizing radiation, but the key is really where they come from. So gamma rays, they come from inside the nucleus. So it's extra energy from in the nucleus, whereas X-rays come from the atom itself. So it doesn't have to be confined to the nucleus. So it's really where they came from. Gamma decay, you'll notice, follows particle decay in many cases, and the question is why? And it's really like after something decays, it's trying to get to a better energy state. But chances are that the new nuclei that's produced is not in an ideal energy state. And so as a result, in order to get to a more ideal energy state, it just releases some of that extra energy, and that extra energy is released in the form of a gamma ray. So, for example, cobalt-60 actually decays by way of beta emission, and it turns into nickel-60, but nickel-60 has a little too much energy, and so it actually also releases some gamma radiation as well. Which leads then to isometric transition, and this is a transition from a metastable state to a ground state. What in the world does that mean? So a metastable state is an isotope that was formed from something else. But it's not yet in that ideal energy state. So isometric transition is where it goes from this like not yet an ideal energy state to its ground state. So for example, I might get sodium 24 metastable. Sodium 24 metastable will actually turn into sodium 24 by releasing that energy in the form of a gamma ray. Or technetium 99 metastable will decay into technetium 99 by releasing a gamma ray. Again, in terms of medical stuff, this one is very important. It's used in medical imaging for detecting heart disease, tumors, things like that. It has a half-life of 6 hours, which makes it wonderful for imaging because it can leave a person's body in a reasonable amount of time. All right, then last one here on this page, alpha decay, what is it? It is often written like this, an alpha particle. It's 2 protons and 2 neutrons. Or maybe a better way to think of it is like this. It's helium-4 2+. You might not always see it written that way, but it has no electrons. It's literally 2 protons and 2 neutrons. This occurs when elements have, Z is our atomic number, greater than 82. Way too many protons in the nucleus. So just a couple of examples of this, like polonium-210 could decompose into lead-206 by releasing an alpha particle. It will also release a gamma particle just to get its energy state down. Or actinium-227 might break down into francium-223 by releasing an alpha particle. So those are some things to know. And then the last thing on here is if I were to just kind of look at a chart of general stability, and I were to look at a chart of the number of protons versus the number of neutrons, and then just for sake here, this is going to be atomic number 82, what we will see is that in general, there's sort of this kind of curved over zone here of protons to neutrons that we would consider stable. You'll notice, while it kind of starts out 1-to-1, it's not 1-to-1 as the elements get heavier. And kind of going along with some of the things that we said is that over here, if you are an element over here where you essentially have too many neutrons, these guys tend to emit beta particles because that decreases the number of neutrons. If you are over here, for example, these guys tend to decay by either electron capture or positron emission because that decreases your protons. And anything over atomic number 82 is going to be radioactive. And so when we start getting up here above 82, these guys are alpha emitters. They decrease the number of protons immensely. All right, that was a lot of stuff, but that concludes the first one.